Hello.
Hello? Hello? Can
Hello,
you hear
Navid.
me?
How are you? Yep, I can
I'm
hear you.
good. I'm good. Yeah, good. That's awesome.
All right, excellent. Okay. So could you tell me about like what you understand and what you don't understand about the Lorentz transformation?
Lorentz Transformation, we actually haven't been taught that at our school, so I don't know.
Okay. So do you recognize these equations now?
No, I don't. We haven't played with those. I don't think so.
Okay. So we've been dealing with length contraction and time dilation, right?
Yeah?
They are kind of included in these equations, and
Kind of.
this is a much more powerful inclusive equations. All right. So these are
Okay.
Lorentz. Hold on. I just need to close the door. I think my baby is crying. My wife is taking care of him, so don't worry.
Okay, that's good. Okay, that's good. Yeah.
Just give me a second.
Okay.
All right. So those are the equations.
Yeah.
So just need to see that this one translates to this one here.
Okay.
So this one is just about a specific coordinate in the S dash frame. So there are two frames. So the S frame is one that's stationary, and there is another frame which is S dash, and this is moving to the right usually
Okay.
at V. V is, it could be like 0.6 c or something, all right?
Okay.
So that's the velocity of, for example, a spaceship, and x is the coordinate, x coordinate of the S frame, and S dash, x dash is the x coordinate of the S dash frame.
Okay.
One thing you need to know is that in the following questions, the frame S and S dash have their usual meanings, which means S dash is moving past S with a velocity v, and when their origins coincide, so when both frames were like synchronized, when the spaceship was just passing this the Earth frame, time is synchronized. So they both start from 0. So t is the time for S frame, and t dash is the time for frame S dash.
Okay.
And I'll just explain what this x here means. So in Galilean transformation or Galilean relativity, we pretty much, I think, let the speed of light equal to infinity.
Okay.
So that means when a signal is produced, it arrives to the object or observer instantly.
Okay.
So have a look. So let's say there was some event here, and the distance from there to there, so the position of this event is x, according to the frame S, right?
Yeah.
Now, there is another frame. Let's say this event happened at time t, at position x, according to this frame here.
Okay.
Now, the S dash frame, according to the Galilean relativity, so this is ignoring all the special relativity, all right?
Okay.
So by this much time, this frame here has moved how much? So distance from there to there is velocity of this frame times by this time, isn't it?
Yeah.
So therefore, according to the S dash frame, he's going to observe. So from here, from how do I write this? From there to there is x, according to the frame x.
Yeah.
What's going to be the x dash? X dash is the coordinate of this event according to the s dash frame.
Okay.
So that's going to be this much, isn't it?
Okay.
That's going to be, oh, hold on, I made a mistake here. That's not true. So according to the frame S, the coordinate of this event is x, and that's that much, right?
Okay.
Yeah, so this event is located that much from the origin of the S frame. So that's x. Okay. So we call the coordinate of this event as x dash, right? X dash. So from there to there is x dash. So therefore we can write x dash is simply x minus velocity times by time.
Okay.
Does that make sense to you?
Yeah, it makes sense to me, yeah.
Yeah, so for example, if there is some event 100 meters away from the this frame here, 100 meters away, there is another person. He's moving at 10 meters per second, and this person observed this event happening around 500 meters away.
Yeah.
At time equals 1, right? Then what's this person going to observe in the S dash frame? He's going to observe that this event occurred at 100 minus 10 times by 1, right? Because he has moved 10 meters, 10 times by 1. So he's going to observe this event to be 90 meters. So that's what this equation is all about.
Okay.
All right. Now the thing is, because we are talking about relativity, so we've been dealing with length contraction and time dilation and things like that.
Yeah.
But this is much deeper than those stuff. So those things that we've been dealing with, the elementary stuff.
Yeah.
This is more comprehensive one. So this gives you length contraction, time dilation, all of that stuff in here.
Okay.
Now, so because we're dealing with special relativity, we have to times this by the gamma. Gamma is given by, so gamma is 1 over root of 1 minus b squared over c squared. So that's what you have to do. Okay. And so you can see that the x dash is given by x and t. T dash is also given by t and x. You see how, we used to just have length is equal to length naught and root of 1 minus v squared and c squared. So, so like x only depended on x, right?
Yeah.
X is like distance or displacement. And time only depended on time, true?
Yes.
So time only depended on time. But in this case, as you can see, time depends on not only time itself, but also the position, the length.
Okay.
So they're sort of combined. So these two are sort of combined together, and that's the Lorentz transformation. So it's a lot more useful stuff. And this is useful when things are like in motion and, a lot more helpful equation, but a lot more difficult to use as well.
Okay.
Now, so you can see that x dash can be turned into delta x dash. So here, this was just a single point. This event was a single point, right? But what if there are two events, So according to the S frame, an event could happen here, and then another event could happen here, see? In that case, the delta x would be the x2 minus x1, so that's x2, this is x1, so in this case it'll be negative, okay? Because it's that one minus that one. And then time, delta t, is x2 t2 minus t1. So time, so let's say this one happened at 5 seconds, this one happened at 3 seconds, then it's a 5 minus 3. So this is always positive, This is always positive.
Okay.
But sometimes this happens in frame S, this can happen first and then this one.
Okay.
But because S dash is moving past, signal from this event can arrive to this person first, and then this one later.
Later.
I mean, the other way around. So the event 2 can arrive to this person first, and then the event 1.
Okay.
It really depends on the velocity and the distance and all that. So, okay. So, but causality should never be broken. That's what I think. If X causes X2, think about it. Like this event causes this event. So there's a causality.
There's a causality.
If there's a causality, then regardless of the frame, you will always observe this one first and then this one.
Okay.
If this one causes this is very important. Okay, so if this one causes this one, and you see this is the signal from here to here at maximum is traveling at the speed of light, isn't it?
Okay.
Then, so I might be wrong though. But I'm pretty sure it's right. So if this one causes this one in any frame, you will not observe this one happening first.
Okay.
But it's only when the signal from there to there is in the speed of light.
Okay.
I think it only also applies when the signal is actually less than the speed. We'll come back to this later.
Okay.
Now, so those are some of the basic ideas. Sometimes you may have to use this one when there are 2 events.
Okay.
When there is 1 event, then you just have to use this one.
Okay.
And this one is this is X dash in terms of the values that belong to the frame S, and this one is the X and T value that belong to the S, but which are in terms of the X dash and T dash. So let's have a look at this question first. So in frame S, an explosion occurs at position 600 and the time is 2 microseconds. Frame S dash is moving at speed of 0.75, 75% of the speed of light in the positive direction. Determine where and when the explosion takes place according to the frame S dash. So here, let's just analyze this. This is frame S, and there is event here, which is 600 meters away.
Okay.
And this one happens at 2, time equals to 2 times by 10 to the power of -6. Now let's find out where the frame S dash is, because the frame S dash is traveling at 0.75, right? Times by 3 times by 10 to the power of, what is it, 8, sure?
Yes.
Yep, and then times that by this time here.
Yeah.
So 2 times by 10 to the power of -6, you know? Then you get 450. So this S dash here, S dash is, hasn't quite passed this event. It's actually somewhere here. So distance from there to there is 450. So if we are assuming Galilean relativity, right, then X dash would be 150, true?
Yeah.
And time would be definitely, time is universal. Time T dash is the same as T. So time is no, so it's going to be the same time, 2 times by 10 to the power of -6. So that would be the case if it's a Galilean relativity. Now all we have to do, let me ask you this. So this is a bit counterintuitive, right? Would this person on the S dash, okay?
Yeah.
So according to Galilean relativity, it's 150 from here to here, right?
Yeah.
Would this moving person see this event's coordinate to be less than 150 or more than 150?
I guess less than.
Yeah, so that's why it's not really helpful to bring in this idea. You see, we're now so used to these 2 equations, right?
Yeah.
And because we know that this is 150 and this is moving fast, and length contracts, doesn't it?
Yeah.
So a lot of people find this very counterintuitive. The answer is about 200, so it's actually larger.
Oh, longer. Why is it longer?
So the reason is, the simplest reason is this. There is a signal coming from here, and it takes a lot more time for this thing to arrive at. So there is definitely length contraction going on, but what overrides the length contraction is, you see this, it takes a certain amount of time to reach here, and that took about this much time. See?
Yes.
Yeah. Hold on. Yeah, but so it must have taken the light to reach certain to take certain time to reach over here, right? But this frame is moving toward the signal, so this guy actually observes this event like way before.
Okay.
Way before. So when the S dash is here, then this guy observed this event already. There's a speed of light. The fact that because of the fact the speed of light is finite.
Yeah.
This guy observes this event much earlier than this person. See?
Mm.
So that's why time has to be time will be a lot less as well.
Less.
Yeah. So ignoring special relativity, just ignore special relativity. You know, length contraction, things like that. That's special relativity, right?
Yeah.
But if you just combine the Galilean relativity plus the fact that speed of light, the speed of light is finite, all right? Then you can understand. Just understand these two here first. Then you see that this guy will observe this event way before, right?
Yeah.
Yeah. So because the speed of light is finite, that's why it'll be about 200. There's also special relativity going on as well. There's a length contraction, but that is expected to be quite small. Think about it. If I just go for 150 here, so if I go for 150, but times this by root of 1 minus 0.75 square, then the length is about, is that 99? That's about 100, is it?
Yeah.
It's actually quite significant. It's a significant reduction, isn't it?
Yeah.
So there's definitely a reduction going on. The length is reduced. But on top of that, this person is... so special relativity has this effect of decreasing the length, right?
Decreasing the length, yes.
That's definitely true.
Yeah.
But there's also we also have to consider the fact that this frame is receiving the signal earlier.
Yeah.
Not over here when the distance between here and here 150, you see? So that's why we have to, so all these two effects are just incorporated into this equation here, right?
Okay.
So you don't have to derive it. So this is a little bit of derivation here, but
yeah.
So just have to memorize it and use it for now.
Okay.
If there's more time, then definitely we can go through derivation, but we don't at the moment.
Yes.
So let's just finish all these questions, and by the end of this lesson, I think you'll get a lot more understanding on this.
Okay.
Yeah. So here's the equation. Gamma, and then x minus vt. So gamma is 1 over root over 1 minus 0.75 square.
Yeah.
And then you see the coordinates according to the frame S was 600.
Yeah.
And this thing was moving at 0.75 c times by 10 to the power of, times by the time. Time is 2 times by 10 to the power of minus 6, right?
Yeah.
I'm just going to plug all of that. So 600 minus, so by the way, this lesson is recorded. So
okay.
you can ask for recording.
Okay, that's good. Thank you.
3 times by 10 to the power of 8. So I'm going to do everything in meters. All right?
Yeah.
Because everything is the 600 meters. So
So
I'm going to assume that's 3 times 10 to the power of 8 here.
Yeah.
And then times by, 2 times by 10 to the power of -6. So that's that bit there, 150, as you can see.
Yeah.
Without relativity, without the, with instantaneous, with infinite speed of light.
Yeah.
Yep, but divide that by the square root of 1 minus 0.75 square, isn't it?
Yeah.
Then you get 226 meters.
Okay.
So what this, the question is, determine where the explosion take place according to the frame S dash. And so according to this guy's frame, this event will take place at 227, was it?
227, yeah, approximate that, yeah.
Yeah, 227 meters. Hold on, I just accidentally closed that one. Yeah, so according to, I'm just going to look at the answer. It says 200 and, so they wrote 226.8.
Yeah.
226.8 meters. Now let's talk about when it takes place according to this one here.
Yep.
So without relativity, without this, it will also take the same amount of time.
Yeah.
But now you just have to use this one here.
Okay.
Okay, so that's equal to T dash is equal to gamma, and this will be the time according to frame S minus velocity of the spacecraft and the position of the event according to the frame S and the speed of light squared. So this one is quite difficult to derive. So if you do this, you will get, so what number goes in here? So it's a gamma. This is a 2 times by 10 to the power minus 6 minus. And what number goes here? Everything has to be meters per second.
Yep.
So this one is
0.75 C times.
Yeah, 75 times by 3 times by 10 to the power of 8.
Yep.
Times by the position, which is 600.
Yep.
Yeah, over 3 times by. So you have to get it all out as 3 times 10 to the power of 8 squared. Okay. So this will give you 7.6 times by 10 to the power of -7 seconds. So which means it takes a bit shorter time, you see?
Yeah.
To reach that. So even without special relativity, actually, so if we just ignore special relativity, but take the speed of light as finite into account, this time will be a bit still. It'll be less than this time here. See, but there's also time dilation effect. Both of them going into influencing this one here.
Yeah.
Do you kind of get that?
I kind of get that, yes.
Yeah? Yeah. So that's what, so there are two things that are playing, influencing this one. Because if there is a frame here, and then this guy here, and let's say there's an event here, and then this occurred at a certain time, then time, let's say time it takes to, so let's say this guy is, so if the speed of light is 10 meters per second, and if this distance is 400 meters, then this will take 40 seconds to get there, but this will take So if this is it's still moving though, right?
Yeah.
It will take less than 40 seconds to get there, right?
Yes.
Even without special relativity.
Yeah.
Yeah. So that definitely does influence time, but there's also special relativity going on. That's why you multiply by this gamma here.
Yeah.
So what happens if we ignore this gamma? I think you will still get some less time. So maybe this bit here is what I'm talking about without the special relativity. Yeah. Anyway, let's move on to 27 here. Just gonna get rid of all this. All right, 27. So frame S dash is moves with the speed of this. An explosion occurs at the origin of the frame S dash when the clocks in S dash reads a 6 microsecond. Calculate where and when the explosion takes place according to the frame S. So this one is, in this case, we have to use these equations here. Yeah, very good. Oops. All right, I should take all of that. Yeah, this one here. That's a pretty simple question. So when and where? So the idea is there's a frame S, but you need to be able to visualize it as well. As usual, this is S. There is another frame, which is S dash, and there is an event over here. It says at the origin of the frame S dash, right? When the clocks in S dash reads a 6 microseconds. So what it means is this spacecraft passed this frame here. So when they were coincided, time was 0. And then according to the S dash frame, this much time spent was spent, and then sort of an explosion happened within the spaceship of the S dash, all right?
Okay.
So the S dash is equal to, T dash, so X dash is equal 0, isn't it?
Yeah.
And time is 6 times by 10 to the power minus 6 seconds, according to the spaceship's frame. Now let's talk about this. So we want to find the X and then T dash. Do you think definitely the X value would be some positive value, isn't it?
Yes.
Yeah, some positive value. So without relativity, of course, this spaceship is moving past how much? 0.98 c, true?
Yes.
0.98 c. So 0.98
Hello?
Yeah. Just give me a second.
Yeah, sure.
Yeah, 0.98 times by 3 times by 10 to the power of 8.
Yeah.
So that's how fast it's going. And if we sort of assume that this time was, there's some time spent.
Yes.
But this time will be different from this time here, right?
Of course. Yeah.
So all of that is given by this formula here. So you just take 0 plus. So just go. That's a 0 plus. That's the velocity times by the time according to the S dash. So 6 times by 10 to the power of negative 6,
Yeah.
If you do that, that's going to be 1,764 meters. So that, I think, would be the distance measured. That would be the position of this spacecraft.
Yeah.
From the spacecraft's perspective, I think.
Not from S's perspective?
Yeah, from S, not from S dash's perspective, because we have to multiply by this.
Yeah.
You see, the spacecraft measured this much time, right?
Yeah.
And then you just times by the spacecraft velocity. So from last lesson, we learned that the velocity
is constant.
Is constant,
yeah.
right? From either frame.
Yeah.
So, yeah, so you can see that this guy is saying that his velocity is this much, and he spent this much, so he must be that much that much meters away from S here.
Okay.
And obviously that's a contracted length, isn't it?
Yes.
But that's the observation according to the S dash here.
Yeah.
So if we just calculate this, we have to times this one by gamma, which is divided by the root of 1 minus 0.98 square, isn't it?
Yeah.
And that's a better answer. So it's 8,000. So let me check the answer. So that is 8.9 times by 10 to the power of 3.
Okay.
So this will be 8.9 times by 10 to the power of 3 meters. So it's 9 kilometers according to the S frame.
Okay.
So that's that one there. And then it says calculate when, right? When does the explosion occur? So let's do some guessing here. Do you think it'll be more than this time or less than this time?
More.
I think it'll be more, right?
Yeah.
But also at the same time, it could be less because the time is running slow in here and time is running faster here, right?
Yeah.
So there are two effects going on. See, why is it more? Because this event is, it doesn't take any time at all to reach the frame S because it is happening. It is happening right at S.
Yeah.
And it takes a little bit of time to get to the frame S here, right?
Yeah.
So that effect makes the time go up, but at the same time, because time is running here slower, more time is spent. More time is spent over here as well because of relativity. There is actually doubling effect. So I believe that time would be more.
Yeah.
There's no increasing effect and decreasing effect. It's both increasing effect, I think. So let's give it a go. So the time here happened. So this here doesn't mean it took that much time to get to this S dash here. It means this is the time measured since the coincidence here, when they were coincided. And then that much time was spent, and this thing happened, right? That's what that time is. So 6 times by 10 to the power of -6, and then you go plus fraction, plus, and then you do a fraction. The velocity is a 0.98 times by 3 times by 10 to the power of 8. That's the velocity times by the position is 0. Oh, that's 0 anyway, right? But that's 0.
Yeah.
So if you just do that, that's just the time. So actually, this simplifies down to, this is question 27, by the way.
Yep.
Time is simply t dash. So that's equal to t dash over root of 1 minus v squared c squared. So this is essentially a time dilation, isn't it?
Yeah.
Yeah. So question 27, the second part, which is the when part, this equation simply simplifies down to time dilation. So why does it simply become time dilation? That is because you see how this event occurs on the S dash at the origin, so it doesn't take any time for this event to get to the S dash.
Yeah.
And that means this exactly happened at that time.
Yeah.
And we want to know if you use that equation, that simply reduces down to time dilation. So if you plug that in, it'll be 6 times by 10 to the power of 6 over root of 1 minus 0.98 square. So it's more time, definitely.
Yeah.
But it is a bit difficult to understand everything that's going on. So that's 3 times by 10 to the power of minus 5 seconds.
Yeah.
But as you do more questions, it'll make more and more sense. Okay?
Yeah.
But one thing you need to really make sure you understand is time interval. Let me just write this
Yes.
down. You need to know that distance is not the same as spatial coordinates. So we'll come back to that later.
Okay.
And also, like this time here, this is when something happened. It's not about how long the signal took. So sometimes it's very confusing. Now, we're going to move on to 28 now. So frame S dash moves with a speed of this much. Calculate the reading on the clocks in frame S dash as the origin of S dash passes at the point 120. Okay. This is frame S dash.
Yeah.
Moving at 0.6 C. Calculate the reading on the clocks in frame S dash as the origin of S dash passes the point. So there is frame, this one here, S here, but there to there is 120 meters. Do you understand?
Yes.
Yeah. So we're going to figure out the time according to the, so event is right over here. The event, what is an event? Event is indicated by the star.
Yeah.
The event is when this frame reaches 120 meters according to the frame S here. So time is simply distance divided by velocity. So distance is 120 divided by, this one is moving at 0.6 C, isn't it?
Yeah.
So we can just figure out, this is 3 times by 10 to the power of 8. So if we plug that in into calculator, this will give you, I'm just checking the answer, 6.666 times by 10 to the power of minus 7 seconds. That's the time. That's how long, I mean, like, that's not really how, that at that time, this one passes 120. Now the question is, according to the S dash's frame, when does that occur? What's the clock's reading on the S dash? So we have to use this S dash, T dash is equal to gamma, and then T, and then minus Vx over C squared. So we use this formula. So what's gamma? That's equal to 1 over root of 1 minus 0.6 square. And then the time is this one here, 6.67 times by negative 7 there, minus, this is 0.6 there, times by 3 times by 10 to the power of 8, times by the position according to the X, the frame S is 120.
Yep.
Over 3 times by 10 to the power of 8 here. So this is not simply time dilation. So if you only have this bit here, that would be time dilation.
Yeah.
Right? So what this one gives you is time is 5.3 times by 10 to the power of minus 7 seconds. Does it all make sense?
Yeah.
Yeah. So why is it not a simple time dilation? Why is it not obviously, less time must have been spent here, right? Less time must have been spent here, because this much time has been spent on the outside. So we have less time here, right? The actual time that is spent on the spaceship is less than this one. But if you only do this part here, that is actually a bit more, right?
Yeah. Yes.
So we need to take this into account. So what does that bit do? Do you conceptually understand this? It's a bit difficult.
Okay. Well, this increases time, this decreases time, right? This one, the one you circled.
Yeah. Let me think about this. Give me a second.
Yeah.
Frame S, speed of that, calculate the reading of the clock. Yeah. Well, we're going to move on. 29.
Yeah.
29. So it gets quite interesting from here. So two events in frame S are such that x2 minus x1 is 1,200, and t2 minus t1 is 6 microsecond. Speed is this much. Calculate this one here and this one here. So we can just use the formula to figure it out. That's pretty easy. So that's this formula here. But conceptually, so if you use that formula to figure it out, so I'll maybe, because we are running out of time, you can, I think you can do it yourself, right?
I can try myself, yeah.
You can just use this calculator, this equation here.
Yeah.
Then you'll figure out that the delta x dash, you see how that's a positive value and a positive value, right?
Yeah.
So if you plug that all in, so it's a gamma and then delta x, so that's 1,200 minus velocity delta t, then what you get is 150 meters. And if you plug into the delta t dash, then you find that this is 4.5 times about 10 to the power of negative 6 seconds. So that's less time than this one. So what does it all mean here? So this is our S.
Yeah.
And I'm going to say that event one was here. That's 1 here. And event 2 is here. And this one takes place at time equals to 6 microsecond. And let's say this one took place at t equals to 0.
Yes, okay.
Now this could have been something like this as well. This is a frame S again. Event 1 here and event 2 here. Okay, so it could have been like that. T equals to T1 equals to 2 microsecond, and then T2 is equal to 8 microsecond. Then the delta T would be 6 microsecond, right?
Yeah.
So this happened first at 2 microsecond, and this one happened at 8 microsecond. That first, and then this one. And then this one happens at 200 meters, and this one happens at 1,400. Then this will give you the same condition here.
Yeah.
This one. Now, but there is a frame S dash which is moving at 0.6 C.
Yeah.
Calculate this one and this one. So obviously, let's suppose that event 1. So this is T0. So this is when the S dash was coincided here, right?
Yes.
So when they coincided, that's when this event happened. So both of them will agree, because both this event occurred at t equals 0. Both of them will agree that the event for this one is t dash would be 0 and t will be 0 as well. In this case, the x dash will be 0 and x will be 0 as well for this particular event here.
Yes.
But not in this case, of course.
Okay.
So what's going on is this one is moving past like this, and obviously what's going to happen is that the S dash will observe, will definitely observe this one first, right?
Yeah.
Because when we consider this case rather than this case over here.
Yeah.
So definitely observe the event 1 first, but then we'll observe event 2 much earlier than the guy who is on Earth, right? This one on the spaceship will observe the event 2 much earlier. So that's what this equation is all about. So, so in this guy's perspective, the distance between the two events is only 150. That's what it means. And the time interval between the two events is only 4.5 times 10 to the power minus 6. All right?
Okay.
Yeah. Now, in both frames, you should know that in both frames, they should not violate causality. So have a look at number 2. Determine whether event 1 could cause event 2. So we know that the distance between two events is 1,200, and the time took is 6 microseconds. So we're just going to divide like how fast signal has to travel to go from 1 to 2. Okay, so we definitely both frames agreed that event 1 happened first.
Yes.
So because you see how delta x was positive, delta t was positive, right?
Yes.
That means t happened first, t1 happened first, and then t2 happened later.
Yes.
For x dash frame here as well, this was positive, right?
Yes.
This is positive as well. That means event 1 happened first, and then event 2 happened later. Both of them agree that 1 happened first, and then 2 happened later. We are asking now this question: could event 1 cause event 2? Okay. So simply divide 1,200 by 6 microsecond, because the time interval between these two events is this much time. So we can see that this is a 2 times 10 to the power of 8 here, right?
Yeah.
Which is less than the speed of light. So therefore we say that that event 1 could cause event 2.
2.
Yeah, because speed of this is less than the gap between event 1 and event 2 is less than the speed of light.
Yes.
So we say that the answer is it is less than. So it's possible. So
possible.
We just write yes, it is possible. Determine whether there is a value of v such that the time interval t dash equals 0, which means could this spacecraft travel at such velocity such that event 2 and event 1 happen at the same time? The answer is no. So we're going to try this one here. So delta t dash is equal to, according to the equation above, it is gamma, and then it's a delta t minus, it was Vx over c squared, V delta x. So in order for this one to be 0, this inside bit has to be 0 as well. So the delta t must equal to V delta x over c squared. Then we can figure out this v here. V is equal to delta t c squared over delta x. So delta t was 6 times 10 to the power minus 6, according to the frame S, original frame, and this is a 3 times 10 to the power of 8 squared, and then over the delta x was 1,200.
Yeah.
So if you plug all of that in, I'm just checking everything here. This is a 1.5 c.
That's greater than the speed of light.
More than the speed of light. Yeah, more than the speed of light.
Yes.
So it is not possible. So we're going to look at question 30, and they're very, very similar.
Wait, can you go down for a second?
Yep.
To the equation you just worked on?
Yep.
T dash, what did you get this from exactly?
I can give you the cursor control. So which one are you indicating? Can you do it? That bit there.
What have you on? Yeah, where did you get this expression from?
Oh, from here.
From here.
Because this is the Lorentz transformation equation, right?
Oh, okay, no, yeah, sorry.
Yeah, so we want that bit.
Want that to be 0, yes.
We want that to be 0, that's right.
Okay, that's fine, yeah, continue.
Yeah, okay.
Yeah.
So in this scenario, there is no velocity such that this can be 0.
Yeah, of course.
In this case, you cannot have any velocity such that this event and this event happens simultaneously according to frame S dash. I'm going to move on to 30. All right.
Yeah.
Same scenario, but this is a bit less time. So according to this frame S, something happens here and then something happens here, and time over here is 3 microsecond, time over here is 0 microsecond,
Yeah.
and the gap between these two is 1,200. Now, what is going to be the delta x dash and delta t dash according to the spaceship? So all the same situation. So this one here, delta, this is delta x minus, what's the formula again?
V times
v delta t. So v delta
V delta x.
So
v
if
delta
we,
that, yeah, sorry.
yeah, v delta t. So this is 825 meters. So according to the guy who is actually moving forward, he is going to observe this to be shorter, the interval between these two. Okay?
Yes.
The length contraction is kind of included in this equation. Now the t dash is, if you also try this, gamma and then delta t minus v delta x over c squared. So if you do this, you get to 7.5 times by 10 to the power of minus 7 seconds. So it's a lot less time, isn't it?
Yes.
So same thing here. You just do that in the same manner as before. Determine whether event 1 could cause event 2. By the way, if we just go back slightly to the previous question,
yeah.
You know how we concluded that event 1 could cause event 2, right?
Yes.
Because where was it? This one here. Because we divided this time by this one, right?
Yes.
What about here, according to the S dash frame? You know, we worked out this to be the distance between the event 1 and event 2.
Yep.
And this is the time interval between event 1 and event 2.
Yes.
So if we divide, so instead of this one here, 1,200 divided by this one, I think we can also do it this way, 50 divided by 4.5 times by 10 to the power of negative 6.
Yeah, you get...
Oh, it's actually a bit more.
Bit more.
Bit more. I thought it could work both ways. Maybe you can't do it. You can't determine the causality using the moving frame. You can only determine the causality using the stationary frame. Yeah. Okay. So we'll just skip this one.
Okay.
Now, if we go back to this, so see 1,200 divided by this one here. So could event 1 cause event 2? So this happened first and then this one later, right?
Yeah.
But with the speed of light, can this travel from there to there in 3 microseconds? So 1,200 divided by 3 times by 10 to the power of minus 6. So in this case, it's no, it's too much. So I would say you cannot.
You cannot. Okay.
Cannot cause event 2 with event 1. So that's the answer for number 2 here. The answer is no.
No.
It's pretty simple, right?
Yes.
Yeah, and now the question is, it's very similar to the previous question. So let's actually consider this case equal there. Okay?
Equal. Yeah.
So so we see that this is a positive here. This is also positive here.
Positive, yeah.
Could there be velocity such that this delta t is negative? I mean, equal to 0. Let's have a look. So then this has to be 0, right?
Yes.
So if you have delta t equals to v delta x over c squared, then you find that v is equal to delta t c squared over delta x, and this can be delta t over delta x and then c.
Yeah.
I actually didn't use this method before. So if you just figure out what this is, right, then so delta t was 3 microsecond.
Yep.
Over, this was 1,200.
Yep.
Times by 3 times by 10 to the power of 8. That's the speed of light. 3 times by, so it's 9 times by 10 to the power of 2 on the numerator.
Yep.
And then divide by 1,200. That gives us 0.75 C. Which means
it's possible.
When this secondary frame is traveling at, instead of 0.6.
Yeah.
So with traveling at 0.6 C, this frame also observes that one happening first and then this one. Mm-hmm.
Yes.
But if this guy is traveling at that much velocity, then what he will see is that they are happening at the same time. But if he goes a little bit faster than that, then he's going to observe that one happening first.
Then
and then that one.
Yeah.
So the delta t dash will be negative.
Yes.
See, this will turn to negative, and this will turn to negative as well. Understand?
Yes, understand.
Yeah, that means this guy observes. It's like, is it possible for delta x to be? I think this will stay as positive.
With negative time, yes.
He's only going to see. So it's actually spatially. He's not going to see this one in front of this one.
No.
He's still going to see that one
behind.
Behind or a little bit.
Yes.
Yeah, it's a bit. I'm going to think about this a little bit more. Maybe I can give you one free lesson, maybe tomorrow, or whenever you like. All right. Okay. If you want some free lesson, let me know. I'm pretty much free on Wednesday, I think. What is your exam?
I'm free on Wednesday. I'm free on Wednesday, completely free, any time of the day.
Okay, sure. Maybe we can have another session on Wednesday.
Yes. Okay.
So this is really interesting. So I'm going to figure out whether this can be negative as well. But if time is negative, this can be negative. If you're faster than this much velocity, you will actually see this guy happening first, and then this one.
Yes.
So one way to actually figure out is actually plug it in here. So you can see that this is a delta t dash is equal to 1 over, I'm going to go for 1 minus 0.8 squared. Okay, so faster than 0.75. And then the time interval was 3 microsecond minus the velocity 0.8 c times by, which is 1,200 over c squared. And then, so I'm going to prove that this is negative. Let's have a look. So it's 3 times by 10 to the power. I'm just going to use my calculator on my hand.
Yeah.
Because I'm a bit faster with this. 1,200 divided by c squared, which is 3 times by 10 to the power of 8 squared. Okay, 0.8 equals 3 times 10 to the power of 8. then 3 times 10 to the power minus 6. Yeah, this gives me negative 2.72 times by 10 to the power of negative 7 seconds.
Yes.
The time interval. So that means this guy will see that one first, and then this many seconds later, he will see this one.
The first.
Yeah. So why is it negative? Because delta t is t2 dash minus t2 dash.
Yeah.
So why would this be negative? Because this is
T1's occurring before T2.
Yeah, this is less than this one here.
Yes.
We can figure out the delta x dash as well using the same thing. So using this equation here. So it is oh, hold on. I only calculated this bit here. I did not multiply by this one here. So this value is wrong, but still negative though, okay?
Yes.
Now, just need to verify that it's negative. This one here is gamma with 1,200 minus 0.78, 0.8 times y. Delta t, which is 3 times by 10 to the power of minus 6 here.
Yeah.
So let's have a look. 0.8c. So I believe that it'll be negative as well. 1,200 minus 0.8 times by 3 times by 10 to the power of 8 times by 3 times 10 to the power of negative 6. It's still positive. Hold on. Yeah, it is still positive, which means, yeah, so it's not negative. But if I make this one 999, I'm going to try that.
Yeah.
It is still positive. Let me double check. 1,200 minus 0.999 times by 3 times by 10 to the power of 8 times by 3 times by 10 to the power of minus 6. Yeah, it is positive, so it's not negative. So just because this one turns to negative doesn't mean that turns into negative as well.
Okay.
So I'll explain the reason why later, maybe next lesson.
Yes.
So I hope this lesson was all right.
Yes. Helpful.
You can try question 31 yourself. So I think
Yeah.
you'll be able to follow now all the solutions pretty well.
Yes.
So try go through all the questions with the solutions there.
Okay.
Yeah. So I'll see you in the next lesson.
All right. Thank you.
No worries.